to a special Halloween edition of Learn with Pi. Today, we're going to use our vector addition skills to go on an adventure. The Dark Lord of Physics has kidnapped you and Pi, and to survive, you must make your way through 5 perilous vector addition problems. Thankfully, you've got your trusty sidekick Pi to help you through it. You and Pi have been tied to a tombstone. You're only able to pull in the directions shown. To knock over the tombstone and free yourselves, you must pull together with a resultant horizontal force of 2,500 newtons. What magnitude of force do each of you need to pull with? We're going to use the parallelogram law. Start by drawing the resultant vector from the tails of our other vectors. We know our resultant will be horizontal and have a magnitude of 2,500 newtons. Now we use the directions of our other vectors to draw our parallel lines at the head of our resultant. Vectors u and p go from our tails to the point where they intersect the parallel lines. Using the properties of a parallelogram, we make a triangle with vector p. Now we can solve for the angle opposite our resultant, since we know the angles that u and p make with the horizontal. Angle r is equal to 180 minus 40 minus 35, which is 105 degrees. At this point, we know all of the angles in our triangle, but we only know one of the side lengths. Luckily, we can use the sine law to solve for both of these. We set up the sine law for both vectors u and r. We rearrange the equations, then fill in our numbers and solve. In the end, we find the forces needed to knock over the tombstone. You need 1,485 newtons, while Pi must pull with a force of 1,664 newtons. You are one problem closer to freedom. You and Pi are locked in a double password protected cell. The passwords are the magnitude and direction of the resultant vector of A, B, and C. You and Pi argue over whether to add B and C first, then add A, or if you should add A and B, then add C. You decide to do it the first way, while Pi does it the second way. We use triangle construction to add vector B to vector C. We draw them head to tail. That lets us draw our resultant. Now we can solve for this angle, because we know that 180 minus 60 minus 30 gives us 90. And since we have a right triangle because of this 90 degrees, we can use the Pythagorean theorem to solve for the magnitude of our vector r. Since we know the magnitudes of the side lengths C and B. Now all that's left to do is find the orientation of this resultant. Since we have a triangle, we're going to work backwards, finding phi first and then using that to find theta. With our triangle, we can find phi by using the tangent, since we know this side length and this side length. So we found that vector B plus vector C gives us a resultant of 38.1 pounds, oriented 6.8 degrees upward from our horizontal. Now all that's left to do is add vector A. For the second part of our question, we're adding vector A to the resultant of our vector from B and C. We draw them using triangle construction, going head to tail, and then drawing our resultant from the tail of our first vector to the head of our second vector. Now we have a triangle, and we can solve for this angle because we know this guy. So with 2 side lengths and the angle opposite what we're looking for, we can use our cosine law. Now all that's left to do is find the angle of our resultant. We're going to use our triangle and the sine law to work backward. And we get that our final resultant is equal to 70.5 pounds oriented at 57.6 degrees upward clockwise from the horizontal. Meanwhile, Pi did the same addition, but she added A to B first, then added C. You both got the same answer. You enter the passwords and escape the jail cell. It doesn't matter what order you add vectors in, you should always get the same resultant. There is a giant pumpkin hanging over Pi's head. You need to pull it up with a vertical force of 400 kilonewtons to keep it from dropping. You can only pull on the cables A and B as shown. Find the magnitude of forces A and B and the angle theta such that the magnitude of force B is a minimum. We start with our triangle construction drawing vector A and vector B, since we know that together they must have a resultant of 400 kilonewtons vertical. From here, we know that we want vector B to have a minimum force. That will happen when vector B is perpendicular to vector A. Knowing that lets us solve for this angle, because we have a right triangle. 180 minus 25 minus 90 gives us 65 degrees. Now we can use our Pythagorean theorem to solve for the magnitude of vector B and vector A. And we find that in order to keep the pumpkin from turning pi into pumpkin pie, we must pull with a force A of 362.5 kilonewtons and a minimum force B of 169 kilonewtons, oriented as shown. You're getting too close to the end, so to make your journey more difficult, this problem has no numbers. What are the magnitude and direction of the resultant to A plus B? We aren't given any numbers, so we have to get our answer in terms of the magnitudes of A, B, and the angle phi. This time to add our vectors, we'll use the parallelogram law. We start by drawing A and B tail to tail. Then we draw our parallel lines. This lets us draw our resultant. Then, using the properties of our parallelogram, we know that this side must be equal to this side. And to solve for this angle, well, this angle must be the same as this angle for B, which is phi, which means that this angle must be equal to 180 degrees minus phi. And we know that the cosine of 180 minus phi is equal to the negative cosine of phi. If you don't believe me, here's proof. Now, to solve for the magnitude of our resultant, we just need to fill in our cosine law. Note that we're using the cosine of 180 minus 80, which is 180 minus phi, which is this angle, but we've substituted negative cos phi. From here, we can simplify our expression for r. Now we have the magnitude of r in terms of the magnitude of vector A and B and our angle phi. All that's left to do is solve for the angle phi. By just doodling an extension along the horizontal axis and making a vertical line from the tip of our vector r, we formed a right triangle. Now that we have a right triangle with the angle theta, we've got a lot more power. So this side length is equal to b times sine phi. And this side length is equal to the magnitude of our vector A plus the magnitude of our vector B times the cosine of phi. Now we know the tangent of our angle theta would be equal to this side over this side. So if we take the arctan of that, we could solve for theta in terms of A, B, and phi. Congratulations! You've found your magnitude of your resultant r in terms of A, B, and phi, and you found the direction, again in terms of A, B, and phi. You're just one problem away from freedom. There are 3 cables pulling on Newton's skull. The force magnitude and direction of 2 of them are known. To move the skull, you need all 3 cables to have a force resultant with a magnitude of 1,000 kilonewtons. What are the minimum force and the direction that must be applied with the 3rd cable? Let's think about this. We want to add 3 forces to get a specified force magnitude. We don't need our resultant to have a specific direction. We only care that it has a magnitude of 1,000 kilonewtons. If we start by adding A and B together, we can figure out how much more force we need to apply with F. And if we put F in the same direction as the resultant of A and B, we can be sure we are applying the minimum force F to get 1,000 kilonewtons. We start by adding A and B using triangle construction. Then, since this would form a right triangle, we know that this angle must be equal to 180 minus 35 minus 90, which gives us 55 degrees. Now we can solve for the angle opposite C, which would be 180 minus 55 minus 20, which gives us 105 degrees. Now, since we know the magnitude of 2 side lengths and the angle opposite vector C, we can use the cosine law to solve for the magnitude of C. After finding the magnitude of C, we need to find its direction. To do that, we use the sine law to first find angle A in our triangle. Then work backward to find phi. We already said that we want the force in our 3rd cable to be acting in the same direction as the resultant of our first 2 cables. That means our 3rd cable must be acting in this direction. So knowing that, what is the minimum force in our 3rd cable that we must apply? Well, since F and C are collinear, we can just do regular addition. And we get that in order to move Newton's skull with a force of 1,000 kilonewtons, our 3rd cable must pull with a force of 206.3 kilonewtons, oriented 23.4 degrees clockwise up from the horizontal. Congratulations! You've worked your way through all 5 problems. There's only one hiccup. You turn to Hi Pa Pi for escaping the Dark Lord of Physics, and she laughs at you because it turns out that she actually is the Dark Lord of Physics, and you have just helped her escape vector addition prison. She's now free to roam the world, torturing people with her twisted sidekicks, Newton and Bernoulli. As penance for freeing her, you'll have to come back and solve more problems. And you'll have to give her treats. Thanks for playing the game that never ends.